So far, we've seen examples of 2D kinematics puzzles. They are largely the same as 1D kinematics puzzles done twice. In this video, we will see some more challenging puzzles and the techniques for solving them. In all the puzzles we've seen so far, the unknown is one component of the kinematics variables, for instance, displacement in x, displacement in y, or so forth. But consider this case. You are shooting a basketball 6 meters from the hoop. The hoop is 3 meters above the initial height of the ball. You throw it at an angle of 45 degrees. How quickly should you throw the ball for it to land in the hoop? We start by drawing a picture. We will consider photo 1 to correspond to a nanosecond after you threw the ball, and photo 2 to the instant it lands in the hoop. We will set upwards and rightwards as the positive directions. The unknown is clearly the initial velocity. We don't know it in either x or y, but we do know the displacements in x and y and the accelerations in x and y. But now we're stuck. We don't have 3 pieces of information in each direction. Until we realize there's something we didn't account for. Let's look at the vector for initial velocity. We don't know its size, but we do know it was launched at 45 degrees. Let's call the size of that initial vector v. That means we could describe the initial velocity in polar notation as v 45 degrees. Now, let's translate from polar notation into Cartesian notation. The x component would be calculated as v cos 45 degrees. The cosine of 45 degrees is 0.707, so we can say that v initial in x is 0.707 v. The y component is v sine 45 degrees. The sine of 45 degrees is also 0.707, so vi in the y direction is also 0.707 v. Let's use this information in our table. When we write it this way, we now see there are 2 things that the x direction and the y direction have in common. One is v, the initial velocity, and the other is time. So let's write out 2 equations, one in x, one in y, that include these 4 variables: displacement, initial velocity, acceleration, and time. The only equation that weaves together these 4 variables is toolbox equation 2. In the x direction, toolbox equation 2 becomes 6 equals 0.707 times vt. And in the y direction, toolbox equation 2 becomes 3 equals 0.707 vt minus 4.905 t squared. We solve these by rewriting the equation in the x direction so that v is isolated. We do this by dividing both sides by 0.707 t. This gives us v equals 6 over 0.707 t. Now we can substitute that into the equation for y. The y equation now gets simplified to 3 is equal to 6 minus 4.905 t squared. We can easily solve for the time. The time is 0.782 seconds. It takes 0.782 seconds for the ball to land in the hoop. And since in the x direction we have a simple relationship between v and t, we can solve for the size of the initial velocity, the speed of the throw. It is 10.85 meters per second. This is a case where we didn't have enough information about the motion of an object in either direction, but we could use an implicit value that was common to both directions, theta, to set up a pair of simultaneous equations, and we solved these to find v. The reverse type of puzzle is one where the velocity is known but the angle is not. Consider this puzzle. A cannon fires at 20 meters per second. The cannonball lands at the same height it was launched from, a distance of 40 meters away. What was the launch angle of the cannon? Again, we'll start this question by setting up a picture. Photo 1 will correspond to a nanosecond after launch, and photo 2 to a nanosecond before it lands. We will set rightwards as positive x and upwards as positive y. The unknown is the launch angle, the angle of the initial velocity. The initial velocities in x and y are unknowns. The knowns are the displacement in x and y and the accelerations in x and y. Let's return to the way we drew our vector for initial velocity. This time, the size of vi is known, but the angle is not. We can still break vi into its components as before. The x component of vi is 20 cos theta, and the y component is 20 sine theta. Let's put these values into our table. Now, in each direction, time and theta are unknown. We can now create two simultaneous equations with t and theta. Let's apply toolbox equation 2 in the x direction. When we simplify it, we get 2 is equal to cos theta times t. Now in the y direction, when we simplify this, we get t is equal to 4.08 times sine theta. We can combine these two equations for t. When we do this, we end up with the equation at bottom. 0.49 equals sine theta cos theta. Now, this would be annoying to solve, but there is something to help us, a trigonometric identity. It just so happens that sine theta cos theta can also be written like this, sine of 2 theta divided by 2. So let's apply this trigonometric identity. A little bit of algebra, and we get theta equals 39.32 degrees. So this was the launch angle. Now, if the cannonball had not landed at the same height that it started from, this puzzle would still have been possible to solve, but more difficult. In this video, we saw examples of more challenging 2D kinematics puzzles. There will be a few further examples of kinematics that we see later on, but we now have enough information to dive into the next big chapter in physics, which is forces.